Hi everyone. So in today's video we're just going to cover some graph theory basics. We'll define what a graph is and the different types of graph you can have, and just some more terminology and applications of graphs. So the first question is, what is graph theory? So in the basic sense of the word, graph theory is just the study of graphs. Graph theory is a mathematical branch of mathematics. And it can be used in many areas. So basically a graph, before we'll formally define it, a graph is just a model of relationships between objects. So we'll just show using these examples right here. On the left we have graph of mutual email exchange between IP addresses. So basically this is just modeling communication between IP addresses, and we've got obviously a very wide variety of IP addresses here, which results in a very large graph. And you can see that some have more communication with other IP addresses, and others may be only communicated with one other IP address. So we'll talk about that more. On the right, we have the Game of Thrones web of betrayals. So essentially, we have characters from Game of Thrones, and then an arrow from one character to another represents that a betrayal of that character. That's not entirely sure how the betrayal is defined here, but you know, when you're creating your own graph, you'll define it in a certain way. So we'll just guess some more about what those arrows mean. Again, like I said, you can define it more, what the lines mean on the right and on the left, and just how you can model relationships between two objects. So we've got lots of applications of graph theory. So just some uses of graph theory in different fields is that graph theory can be used to visualize data and relationships, as I said before. So rather than listing out lots of data points and different properties of them, it might be helpful to represent it as a graph so that people, maybe people who aren't in your discipline or people who don't know all the terminology of your field, they might be able to understand better what they're looking at if they can see it modeled as a diagram in a graph. And it'll show the relationships between two different objects across the whole system. So also graph theory can be used to find structures in a network. So I say, for example, finding community structure, which we'll talk about more later, but this might, for example, you might have in a graph, you can find one community, one cluster of nodes is very tightly connected over here, whereas you have another one over here. And using graph theory is an easy way to apply mathematical processes and algorithms to your network to maybe reveal things that you wouldn't be able to do by just listing out those data points. So we've also got some real-world applications listed here. So the first one we mentioned is studying the transmission of epidemics, which is a hot topic right now. But for example, you can model a network, a social network of people, and you can show the relationship between two people where one person may transmit the virus to another person, and then of course that person may transmit to another person, and then well, it goes all the way out. So you can model this as a graph to show the overall structure and maybe who is transmitting it more if you've got a wide party or something where a lot of people will get infected. It's a clear visualization of that kind of transmission. So another example is transportation routes, to find the most efficient path. So as I said, it can be easier to find efficient routes and shortest path problems using graphs because they're an easy way to model it and you can apply math processes to them. So also, just as a base example of transportation, you can even consider maps to be a graph. So if you have two locations, the roads connecting those locations will be the edge, and then that'll just form one large graph. Another example we have are protein-protein interactions in biology. So really you're just modeling the interaction between two proteins, and you can use graph theory to show this and maybe find out which proteins are more alike in terms of their interactions and what other proteins they interact with, which can be very helpful. Last example we have is social analysis of street gangs. So you can model a street gang maybe as who recruits who, and then if you perhaps have one person who recruits lots of people, if law enforcement is looking to find out who might be the most central person into that gang, this is an easy way to figure out or to model which people they might want to focus on. So now we can formally define a graph for graph theory. So we call generally a graph G, and it's defined by an ordered pair V, E. So the set where V and E are both sets. So the set V is the set of nodes, or vertices is another word for node. So a node is these points right here. We have 0, 1, 2, all the way up to 5. So the node in hand is the object of your system. So if you are looking at the social network, each node would be one person, right? So let's say you're looking at Facebook. Each Facebook profile is one person, represents one person, and each of those people would be represented by a single node. So then we look at the ordered pair E, which is the set of edges or links, which is another word for edges. We might use those interchangeably. So the edges are these red lines right over here, where it connects, one edge connects two different nodes, or has two ends, so it connects two nodes together. So we've labeled this one edge 1, 3. So an edge is represented also by an ordered pair of the first node, the second node. So you see that this edge, I don't know if you can see my mouse. This edge connects node 1 to node 3, so that's why we call it in parentheses 1, 3. And so the edges, the meaningful definition of edges is that they represent the relationship between people. So back to our Facebook example, if you have Facebook profiles as the nodes, then the edge between two nodes may be that these two profiles are friends with each other, like formally click the button friends on Facebook if you have a Facebook. So what an edge represents the relationship between those two people. And so of course, one person is not only friends with one other person. Let's say you have person 1, they are friends with 1, 2, 3, 4, 5 other people. So that means that they have 5 edges connected to connected from that person to other people. So essentially, it's a very basic concept of nodes are the objects and edges are the relationships between those objects. So kind of going back to one of the examples before, if you have, let's say, a map, the nodes will be the locations, maybe cities or buildings, where the edges will be the roads. So that road is the relationship showing that you get to this location from this location using this road. So that's a very physical interpretation or use of an edge. But yeah, so there are many different areas of science and social sciences that you can use graphs to model the relationships between objects. So we will define the number of nodes to be n, a capital N. So in this graph right here, we have n equals 6 because there are 6 nodes, 0, 1, 2, 3, 4, 5. And we'll define the number of edges to be equal to L. So L is equal to 10 in this case, in our graph right over here, because there are 10 edges. And so at the bottom, we've listed the sets explicitly. So we have V, which is V is the set of nodes. V is equal to the set of node 0, node 1, node 2, 3, 4, and 5. All right, and then E, which is the set of edges. E is a set of ordered pairs, because each ordered pair represents one edge. and it's just each edge. We've got 10 different edges here. So we'll talk a little bit more about what you can and can't have in a graph. Right now you can see right away that we have a self loop or self edge right here, which is just an edge from 5 to 5. And this is perfectly reasonable. You can use this in a graph if you'd like to. Other places it might not be appropriate to do that, but you can create it if you like. So, like I just mentioned, you have self loops, which is just an edge from a node to itself. I have down here a click. A click in a graph is a subset of nodes that are all connected to each other. So if this whole thing is a graph right here, then this little click of nodes 5, 6, 7, and 8, you see that each of these nodes connect to each of the other nodes. So 5 is connected to 6, 7, and 8. 6 is connected to 5, 7, and 8, and so on for the last two. So that's a click. So if you were to have a 5 click, that would be 5 nodes, all of which are connected to each other. If you had a 100 click, that would be 100 nodes, all of which are connected to each other. So another thing I have here is connected components. So the way we're looking at it, you can kind of see from the numbering of the nodes, because we have 0 all the way up to 8. You can tell that this whole thing is considered to be one graph. So this is all one network. And we see that we have 2 connected components. So on the left, we have nodes 0, 1, 2, 3, and 4. And they form a connected component because these nodes are all connected to each other, which means that there's at least one edge between each node to one of the others. And we have a connected component over here, nodes 5, 6, 7, and 8, where these are all connected to each other. But you see that this component and this component are not connected. There is no edge between the nodes on the left and the nodes on the right. So we call these two groups of subsets of nodes a connected component. And as a whole, the graph is disconnected. Okay, so some other parts that we need to learn. We have the adjacency matrix of a graph. The adjacency matrix is just another way to represent the graph. So you see that over here we have the graph represented visually as points and lines, which is how we covered before, but we can take the information shown by this graph and represent it the same exact information as a matrix. So the adjacency matrix is defined by this. I'm sorry if my mouse is all over the place. I can't really see it when I move it. Is defined by an element of the matrix right here. So we put a 1 in the cell in the element Aij. If there is an edge from node I to node J, and a 0 in the element if nodes I and J are not linked together. So if there is no edge between node I and node J. So let's just pick a random edge here. We'll start with the edge 0 to 1. So edge from node 0 to node 1. So visually we can see that there's an edge here, but if we look at the adjacency matrix, we see that if we go to row 0, column 1, so it's row 0, column 1, there is a 1 here because there is an edge going from node 0 to node 1, right? And then let's take another example. Let's look at the edge from 3 to 5. So again, we see that there's an edge going from node 3 to node 5 on our graph. And we can also look at this on the adjacency matrix. We go down to row 3. So this is 0, 1, 2, 3, row 3, all the way over to column 5. So this is column 0, 1, 2, 3, 4, 5. So that's right over here. We have a 1 because there is an edge from node 3 to node 5. And then if we were to look between 2 and 3, you see obviously there's no edge between node 2 and node 3. So if we look at element A, 2, 3, there is a 0 in this spot because there's no edge. So you can see that. And right now, two things I'll point out is a lot of the time we will have a symmetric matrix, and I'll explain when it's not symmetric, but at the bottom I'll say that in an undirected graph, the adjacency matrix A is symmetric, and this is because the edge from node 1 to node 2, in this case, is the same as an edge from node 2 to node 1, right? And so there are cases where that's not true, which we'll cover very soon. But right now you can see that in the adjacency matrix, there is this diagonal line the matrix flipped across the diagonal line is exactly the same, which is symmetric. And also we see that right now we do have a self loop. And so this self loop from node 5 to node 5 gives a 1 in the very last entry, which is the entry of row 5, column 5. So we have a 1 there. But as I said before, in many cases it's not appropriate to have self loops. It maybe wouldn't make any sense. So if that was the case, then oftentimes you'll find that the main diagonal of the adjacency matrix will be all zeros, right? So this will just, if you see that the main diagonal is all zeros, you know that there's no self loops. If you see that there is a 1 in this diagonal, then there are self loops somewhere. So the adjacency matrix is useful because it's a way to, a different way to store the graph as a data structure, as I mentioned right here. And it can be an easier way to apply mathematical functions onto the graph. So there are some ways where you might store it as a list of edges between nodes, and then maybe there's ways where using the adjacency matrix, you might be able to perform some linear algebra operations on that matrix, which can give you some new insights onto the graph. So it's really just these two objects, this visual graph right here and this matrix, the adjacency matrix on the right, those represent the exact same information. But it is a very useful way to gain some more information from it by looking at it as a matrix. So another important, I don't know if I can move my camera right here. You might not be able to see the words underneath. Well, I'll have the lecture slides posted. You're not really missing much right now. But another topic under graph theory to learn about with graphs is the weight of an edge in a weighted graph. So the weight of an edge is some meaningful number associated with that edge. So I've got some examples here. For example, if you have the weight representing the number of phone calls between people, so let's say our graph, we have the nodes are representing people, and the edges are representing a phone call between one person and another. So if we have, right over here, we've got person 1, person 2, and they have an edge between them, which means that there was a phone call between them. So the weight of that edge might represent the number of phone calls between people. So in this case, if we look at edge 1 to 2, then the weight, which is 6 in our example right here, that might mean that there were 6 calls between those two people, right? And so really what that means is that that edge has a heavier weight. So for example, we'll just look right here, if you see between nodes 3 and 4, we have an edge with weight 3, so that might mean only 3 phone calls between those people, whereas between 1 and 2 have 6 phone calls. So, in many cases, a higher weight will indicate a stronger relationship between 2 nodes. So, practically speaking, maybe person 1 and person 2 are a lot closer than person 3 and person 4 because their weight is 6, they have 6 phone calls between them, whereas the other edge has a weight of 3, there's only 3. So you can see why that's a meaningful number. So another example might be distance between locations, where the higher the weight of the edge means the further away those 2 locations are, right? So, I mean, this might come from a practical standpoint that you're not going to draw a graph that's humongous if you can just draw it very plainly and then use a number to indicate how far away they are. And you can use those numbers to find other information about the graph. So last example, we have travel costs between the cities. So this might maybe go hand in hand between distance, but let's say you have, where's my mouse? Again, we'll just use the edges 1, 2, and 3, 4 again. Let's say that this 6 might represent $600, all right? So that'll mean that to get from city 1 to city 2, and vice versa, city 2 to city 1, it costs $600. Whereas to get from city 3 to city 4, it costs only $300. Okay, so the weight of an edge can be very meaningful and is often a very useful tool in making graphs that'll represent real data. And so the way that we will record the weights of the graph is in the adjacency matrix, whereas earlier, let's see if I can go back to the other slide. Earlier, we filled in the adjacency matrix with just zeros and ones. So the zeros represent no edge between 2 nodes, and the 1 represent 1 edge between 2 nodes. So if you look at a weighted graph, the adjacency matrix, rather than filling it with zeros and ones, we'll fill it in with the weights of the edges. So we still have a 0 representing no edge, because if there's no edge, then the weight is going to be a 0, because there's no edge to begin with. Whereas now, the representing an edge is shown by the value of the weight. So before we talked about edge 0, 1, we have a weight of 7 here. So again, this could mean a number of different things, maybe 7 phone calls between these people, or 7 miles between these cities, things like that. In the adjacency matrix, we fill in that entry of row 0, column 1 with a 7. And then, of course, we also have row 1, column 0 with a 7, because right now it's exactly the same. So that's what the weight means. Again, this is a very useful tool to have for lots of applications. So something we hinted at before, which we saw in one of our first examples of the betrayals, we would see arrows rather than lines, is the difference between a directed graph and an undirected graph. So far we've been using the example of an undirected graph, which we'll see on the right over here, and in an undirected graph, each edge is just represented by a line. So this line means a relationship between 2 nodes will go both ways. So whatever relationship is from, is from node 1 to node 2, the exact same relationship is from node 2 to node 1. So if that's, again, let's say we're using a graph to represent location or cities, or like a map of roads, then intuitively you know, of course, that if there is a road from, I mean, maybe this isn't exactly true, but most of the times, if there's a road from city 1 to city 2, then there is a road from city 2 to city 1, right? So that's an undirected graph. So mathematically, we see that this is shown by edge I, comma j is exactly equal to edge j, comma I. So they mean the same exact thing. Edge 1, 2 is the same as edge 2, 1. So on the contrary, we now introduce the concept of a directed graph. So in a directed graph, it's not the same. So we'll look mathematically first that edge I comma j is not equal to edge j comma I. And practically speaking, this can mean different things. So let's say that we have a graph that represents phone calls between people. So this kind of comes back to how are we exactly defining these relationships. So if we define an edge, the relationship between two people, to just be there were phone calls or they talked on the phone, maybe we would use an undirected graph, because if person 2 talked to person 3 on the phone, then it goes hand in hand that person 3 talked to person 2 on the phone, right? But if we were to change the definition of our relationship so that an edge between two people represents one person called the other, which actually gives us a little bit more information than the first example, then it's not the same to say that person 1 called person 2 means person 2 called person 1. That's not true, because of course only one person is clicking the dial button, so you can't say that just because someone called someone else that it's the same way backwards. So in these situations we'll use a directed graph, and rather than lines representing edges, we use arrows. So the arrow represents the relationship from one node to the other in the direction of the arrow. So for here, we see that there's a relationship from person 1, or I'll just say node to make it more general, from node 1 to node 2. But of course, we see that there's no edge from node 2 to node 1. And so this means that the relationship doesn't go backwards. And in this case, we can also see that we can still draw relationships exactly how we would as an undirected graph. And we see between node 0 and node 1 that we have two arrows, one going one direction and the other going backwards. So if we use the phone call example before, this might represent that they each called each other, maybe at two separate occasions. And just like before, we can still have self loops. Who knows what that might mean? You call yourself, I guess. People might do that. Yeah, so this concept of a directed graph is, again, very useful in real applications, and can give you even more information than you had with just an undirected graph, and can still be using the same kind of math procedures on it. So the undirected graph, we had an adjacency matrix, and in the same way we have an adjacency matrix for directed graphs. And the only difference, they would be exactly the same. The only difference is, how I mentioned before, there's no need for the adjacency matrix of a directed graph to be symmetric. And this is, you, of course, might already see this by now, because the relationship from one, from one node to the other does not have to go the same way backwards. There's no need, or it's not necessarily true that you'll have the same entry or the same value in entry row I, comma row j, row I, comma column j, as you would in column I, row j. So I'll just show this from the example that we have on the screen. Let's say we're looking at edge 1 to 4. All right, so we have an arrow from node 1 to node 4. We can see this on the graph in the adjacency matrix, that we go down to row 1. We go down to row 1, and then all the way 0, 1, 2, 3, 4, all the way to column 4, and we have a 1 there because we have an edge from node 1 to node 4. But this time, if we look the other way around, already we can see there is no edge from from node 4 to node 1, and we can see this on the adjacency matrix. where we look at row 4 to column 1, and there's a 0 there because there is no edge going in that direction between the two nodes. So if this was an undirected graph, it would be symmetric, but since it's not, as a directed graph, the adjacency matrix is not necessarily symmetric. Okay, so now we come into another important property of graphs, or terminology that you should know, is the degree of a node. So the degree of a node is the number of edges attached to that node. So we'll talk about a little more, but we'll just look at the example we have right here and we define the degree of node I to be denoted by k sub I, right? So we see k sub 0 represents node 0, and the degree is 3. And looking at the graph, we can see that because here's node 0, and we have one edge connected to it, 2, 3. There's 3 edges connected to node 0, so its degree is 3. And for the rest of these, it's kind of similar. I'll just go down to node 3. So we see that K3 is also 3 because if you look at node 3 here, there are 3 edges connected to it. So let's take a look at the last node, node 4. And this node has a degree of 4. If we look at it right here, we have node 4 is connected to one other edge, has one other node, one edge, 2 edges, and then we have a self loop here. And so this is going to count as 2 edges, at least in terms of degree. And so this definition can vary in different places. So some places might say that, oh, it only counts as 1, so then the degree would be 3. But at least for right now, we're going to count this as 2 to contribute 2 to the degree of that node. And this is because if you look at it, it'll help a little bit with our mathematical formulas that we'll apply in later modules. And also just to look at it visually, we're kind of looking at it based on the end of the edge. So there's 2 different ends, so that's going to count as 2. So that's the degree of the node. The degree of a node is very useful in the mathematical algorithms that we can apply in graph theory. And this is just something that you should keep in head. You can list each node with the degree of that node, kind of like we did here. And so it really just is about counting the number of edges attached to that node. So, okay, so before how we looked, that was for the undirected graph, right? So you see right there, each edge contributes the same thing for the undirected graph. For the directed graph, it is a little bit different to count the degree because there is a difference from going out of a node and coming into a node. So because of this, we define 2 different terms. We have the incoming degree and the outgoing degree of a node. So this is very intuitive. You have the incoming degree of a node is represented or is denoted by ki in. So that's the number of edges pointing to that node. Okay? So we'll look as an example, node 2, right down here. There are 2 edges connected to it, but the only edge coming into node 2, pointed towards that direction, is from node 1. So the end of the arrow is looking at node 2. So that means that we will have K2 in is equal to 1. Okay, so in the same way, we also define the outgoing degree of a node, which is just the number of edges pointing from that node to other nodes. So again, let's just look at node 2 again, because it's pretty simple. Just like we counted this edge to be an incoming node, to be an incoming edge, this edge from 2 to 4, would be contributing to the outgoing degree of node 2. So k2 out is equal to 1. Okay, and so from there, we can define the total degree of a singular node, and that's just the sum of the incoming degree and the outgoing degree of that node, right? So ki, which is just the degree, the total degree, is equal to ki in plus ki out. So right here we have a little chart that just represents the degrees of this graph on the left. So let's just select one example. Let's look at node 1, okay? So node 1, first, we look at the number of edges that point to node 1. So you can see that there's only one edge that points to node 1. That's edge 0, 1. And so that means that the incoming degree of node 1 is 1, which we have on the chart. And in the same way, next we look at the outgoing degree of node 1, and you'll see on the graph that there's 4 edges going out of node 1 to other nodes. So that means that the outgoing degree of node 1 is 4, and when we sum those up, 1 plus 4, we get 5, which will be considered the total degree of node 1. And you can do this for every node on the graph. All right, so the next topic that we'll cover is a path between two nodes. So as we define at the beginning, we see that a path between node I and node J is a sequence of edges to follow to go from node I to node J. So before we look at the length and things like that, I'll just kind of draw or point out a path for you here on the graph. So let's say we want to go from node 2 to node 3, right? Actually, let's not do that. I just looked at the example and I realized that that's the exact example that I have on the slide. So let's just take a look at this third bullet point right here. Yeah, so the example paths from node 2 to node 3. So a very simple way to do this is you start at node 2, and then you follow the first edge, which will be the edge from node 2, to node 1, right? And then, to get to node 3, you follow the next edge, which is from node 1 all the way to node 3. So you just traversed two different edges, so node 2 to 1, 1 to 3. So that represents path 2 right here at the bottom. So there are a number of different ways, or a number of different paths that you can take from one node to another. And the way we might be able to distinguish these paths from each other is by the length. So the length of a path between two nodes is the number of edges that it contains, right? So if we look at this example from node 2 to node 3, we saw the very simple example of path 2, which was just going where's my mouse? From node 2 to node 1, and then node 1 to node 3. But another path that we could take, if we really wanted to, is we could go, let's follow this. We're going to follow path 1 now, right? We can go from node 2 to 1, node 1 to 0, node 0 to node 5 back to node 1 to node 4, and then node 4 to node 3. So we have followed a sequence of edges to get from node 2 to node 3. So we have drawn a path, right? From node 2 to node 3. But as I ask down here, which one is more efficient, right? So which one, realistically, like let's say these are locations and you had to walk this path, which one are you really going to take? It's just not very feasible or practical to go path 1, because why would you do that? Where the length of path 1 is 1 edge, 2, 3, 4, 5, 6. The length of path 1 is 6, right? And the length of path 2 is 2. there's only 2 edges in path 2, right? So if you're going to talk about which one is more efficient, you're probably going to go with path 2. But these are just 2 different examples of paths, right? And of course, you can do lots of different ways. You can go node 2 to 1 to 4 to 3, which is longer than path 2, but shorter than path 1, and maybe there's some reason you'd want to do that. So the concept of a path is, again, very important in different areas of where graphs can be used, because it just shows the different ways that nodes are connected to each other and the different ways that you can go from one to another, and those ways might be useful. So as we've talked about, we have which one is more efficient, which path you might use. This goes hand in hand with the concept of the shortest path, right? So the shortest path between 2 points is a path with the smallest length. So right here we look before the shortest path between node 2 and node 3 is going to be that path 2 from earlier, which is 2 to 1 and then 1 to 3. Right? There's only 2 edges in that. And we define the distance between 2 nodes to be the length of the shortest path. Right? So in this example, the distance between node 2 and node 3 is 2, because the length of that path, of that shortest path, is 2 edges, right? So the distance is just going to be equal to 2. So we have a definition, or the notation here is dij is equal to the distance between node I and node j. And so nodes don't have to have one singular shortest path. So for example, we can look at, let's say, getting from node 1 to node 3, right? We can get there. Oh, no, I'm sorry. So actually scratch that, okay? I didn't say anything. So we'll just look at these shortest paths real fast. Okay, so node 1 to node 2, we see the shortest path is very simple. We're just taking one edge, which is from node 1 to node 2. So that means that the distance between these 2 nodes is 1. And then we'll look at a different example. We have node 2 to node 5. So the path that we take, the shortest path, is we go from node 2 to 1, so that edge, and then we take edge 1 to 5. So that means that the distance, since that's the shortest path between the 2 of them, the distance is equal to 2. Of course, if we wanted, we could take a different path, which maybe we could go 2 to 1, 1 to 3, 3 to 5. But then the path, or the length of that path, is 3, and that is not the shortest path, because as we just spelled out, we can take this path, 2 to 1, 1 to 5. So the distance is considered to be 2. And as I was saying before, I should have trying to find a good example here, but there doesn't have to be only one there isn't always only one shortest path between 2 nodes. But the shortest path or if there are 2 shortest paths, they will have the same length. Because obviously if one path is longer than the other, then one of them is not the shortest path, right? But if there's 2 different paths that have the same length, that is the shortest path, they will be the same length, which means you still have the correctly defined distance between those 2 nodes. And so we can record these shortest paths into a distance matrix where it looks kind of similar to an adjacency matrix, but it represents something different. So we record the paths from nodes. We record the paths from nodes into this matrix as the shortest path, which would be the length, or the length of the shortest path. So, for example, if we're looking, let's say from let's say from node 2 to node 0, okay? So we see from the graph that the shortest path is from 2 to 1 and 1 to 0. So the distance is 2 because we traversed over 2 edges. So if we look at the distance matrix, we can see this represented. We go to row 2 because we're starting at node 2. So 0, 1, 2. And we stay at column 0 because we're going to node 0. And we see that the number that we have here is 2 because that's the distance between those two nodes, or the distance from node 2 to node 0. And this is a symmetric matrix, but that's just because this is an undirected graph right here. If this was a directed graph, then the matrix does not need to be symmetric, similar to the adjacency matrix, because in a directed path, you might not have a distance, or you might not have a path from one node to the other, whereas you could have it the other way around. So it might not be symmetric. And I'm noticing here that I have a self loop from 5 to 5, so there should be really a 1 in this last entry here. Because we do have a path from 5 to 5, whereas the other ones, there's no path, there's no number of edges that you have to follow. No, sorry about that. That was wrong. Well, I didn't say anything. This matrix is correct. So the reason why I was gonna say that, which I said incorrectly, that there should be a 1, was because we see that there is a path from 5 to 5 traversing this edge, which is edge 5, 5. But, of course, that's not the shortest path because 0 would be considered the shortest path because if you're already on that node, then you're there. You don't need to take a path to get to it, right? So if, let's say, for example, let's say that nodes are representing buildings, right? So if you're already in building 5, to get to building 5, you don't need to take a path, even if there is some kind of loop in the backyard, right? You don't need to take the path, you're already there. So since this distance matrix is recording the shortest paths, even if there's a self loop, you're still gonna have a 0 there because the shortest path is to not take a path at all. So that's why we have a 0. So forgive me for that mistake. But I'm glad I didn't just leave it at that. Anyway, so we see that the distance matrix just records the shortest path, or the length of the shortest path, really, which is the distance between two nodes. Okay, so that's the end of the graph theory basics. Let me go back right now to the shortest path page, because we're going to have a video online of an algorithm that you can use on a network to find the shortest path between one node to another, right? So for every node or for every pair of nodes in the graph. So this is called Dijkstra's algorithm, and I would explain it here, but there's so many great videos online available for you to look that explain it really well. So I'm just going to link to one of those videos. I'll post that online, which you can look at. Yeah, so the algorithm will be used to find the shortest paths from node to node, which is an important topic you may have seen already, but it's good to look at and refresh. Anyway, yeah, so that's the end of the basics for graph theory. If you knew nothing about graph theory before, then this should have been a good introduction into what is a graph, different parts of a graph, and different uses of graphs. So I have a reference right here, the networksciencebook.com, which I'll link. I might post a link to that in the web courses, or you can just go from the slides. So that's a really good book, which will cover kind of the same things we did in the first chapter, and some more uses of graph theory in real-life networks. Okay, so that's it, everybody. Thank you for watching, and hope you learned a lot about graphs. All right, goodbye.